If you all heard the last speaker's presentation, there's 3 things I want you to remember when I talk. I want you to remember the word intuition. I want you to remember the word relationships. And I want you to remember the word narrative. These are very, very important with data analytics and how you represent your data. And that's really what the Allosphere is all about, how we can use multisensory computing to represent your data. So let me take you on a little trip into the future where creative thinking, multisensory computing, and data analytics go hand in hand. Imagine a time when you could hold voluminous amounts of information in the palm of your hand, where you could pull out of thin air 10 years of your company's inventory, make it visual, sonic, interact with it, where you could feel the weight of your data, whether it's a complex quantum equation, the human genome, an abstract work of art, or your company's worldwide inventory. Imagine a time when technology becomes so transparent that you can walk through and understand complex patterns in your information the way that you see complex patterns in nature, intuitively, artistically, controlling this just the way an artist finds their inspiration. Well, there's a team of us researchers at the University of California, Santa Barbara. We are artists, scientists, and engineers, and we're trying to make this dream a possibility. We work together creatively in concert, mapping very abstract and voluminous amounts of data in time and space, much the same way that an artist or composer would create a work of art. Now, I'm immersed in unfolding complex systems, and in order to do this, I built an instrument, a very big instrument. You kind of see it there on the screen. It's a 3-story metal sphere in an echo-free chamber. You walk into the 2nd story, you're on a bridge, suspended in 4 pi stereo radians of visual information. 30 researchers can stand on that bridge, pick up wireless devices, and perform their data, much in the same way that a jazz ensemble would walk on stage and perform their music. Very complex information intuitively. This is a most important aspect of this data. Working your right brain and your left brain. What do you do when you have a tremendous amount of information, and that information is charts of numbers? How do you visualize that data? How do you sonify that data? Yes, see and hear that data. Well, think about it this way. Our bodies are filters, and all of our senses filter frequencies. Frequencies in the visual domain that are light, frequencies in the audio domain that are sound, frequencies that we feel, vibration, and I'm sure, even though I've talked to some of my chemist friends, smell and taste can be mapped into frequency relationships. Now, if all this mathematics, and we heard it's not about mathematics, it's about relationships, right? Well, it's about the relationships of these mathematics to your senses, to your intuition, how you can understand and know and feel this data so that it's second nature to you. So let me map it a little bit into your community, because I work a lot with scientists, and I think with scientific visualization, it's a lot easier to understand frequency and vibration. An atom vibrates, it makes a phonon, which is a very, very high frequency that almost acts like an audio waveform. So I could take that frequency and through fast Fourier transforms mathematically map it into the audio domain. So how would I do that with data visualization? Well, frequencies have 2 things in common. A frequency means how much or how loud, and how many. What's the vibration? So if you start to map this into your information, you start to take data that's coming in, the data flow of what's happening on the web, what's happening in your particular marketplace. You map this into a mathematical construct, you can start to assign different types of sound frequencies, different types of visual frequencies to this data and to this information. These are the things that we do at the Allosphere instrument. We work, as I said, a lot with scientific data, but we also work with economic data. Right now, we're mapping 3 different currency exchanges relative to gold. And we've got the past 6 years, and you should see and hear the 2008 crisis. It's really, really exciting. Remember this, when things are going fine, when everything is vibrating uniformly, you get a pitch. As soon as things start to vibrate randomly, you start to get noise relationships. This is not erratic. There's a frequency continuum. And you can use this to map your data. You can get to the point of being able to look through your data and try to understand, but the most important thing is to be able to forecast what might happen. And I think that's the most important thing to all of your industries. So without further ado, I want to show you the instrument. I'm going to fly you into the instrument. I'm going to play a video for you that's going to show you the research we're doing in the Allosphere instrument. And then I'm going to show you some very interesting video of what my PhD is working on right now, a mathematical language that maps audio into visual information, visual into audio information. So you'll start to understand that we're building this language that we call conjugate space mapping. So I'll start with this, and then if I have time, Jim's going to signal me, I'm actually going to perform for you in real time from my laptop a hydrogen atoms, electron, in superposition. Now, you've all heard of Schrodinger's cat. I'm going to play the Schrodinger equation for you, and I think you're going to start to understand how very complex information can become intuitive to you. By the time you leave here, you're going to understand basic quantum mechanics. Now, that was a feat for me as a composer and a musician and an artist. When I could see it, I could feel it, and it was tangible to me. It became real. Maybe this is a way that we can really have a change of consciousness, right? If we can start to control very complex information intuitively, what we might be able to come across. But we got lots of data to worry about, so without further ado, I'm going to start the video and let you know what building we're in. We're in the California Nanosystems Institute. I'm working with physicists, Nobel laureates. I'm working with material scientists. They have machines that measure data. I take the data from the computational scientist and map it. There's the building behind you, Ealing's Hall. Love to give a pitch to Virgil Ealings for naming the building. Now we're going to do a virtual fly-through into the instrument, and then you're going to be standing on the bridge with me. And this is really a sphere. It's not a room. It's an instrument. Big display. Here we are. We're on the bridge. 30 researchers. We're going to go out the door and up the top so you can see it's a real sphere. And then we're going to fly back down in, and you're going to see researchers standing on the bridge, watching and hearing electrons spin, or flying through a lattice of atoms and new materials for transparent solar cells, or flying through the cortex of my colleague's brain, real fMRI data, looking at the tissues as landscapes and hearing the blood density levels as sonic information. This is the kind of research that we do in using our computational framework for multimodal mapping. Here on the bridge, there's a physicist, there's an engineer, there's a media artist, and a cognitive scientist all working together. We never work apart. It's all about relationships. I know how to map the data, but they know what's important in their data. Nobody should ever go away and leave their data with me alone and untouched. So I'm going to take you now through 5 research projects that are going to take you through macroscopic brain data all the way down to electron spin. It's our first research project, real functional MRI data. We call it AlloBrain. It's the cortex of my colleague's brain. He was going into fMRI machines and registering his blood density level every time he saw something he thought was beautiful. We call it beauty in the brain. Now, these little agents, no, they're not really in his mind. Those are 12 intelligent computer agents that are doing agent-based data mining. The little rectangles are looking for blood density levels. They're giving that information to the nurse, the little triangles that go fly to the place in the brain where the blood is the densest. That means that's the part of the brain that's thinking, okay? So you can imagine neuropsychology, medical applications that can happen here, and how you can map it into your own data as well. We're flying off to the left of my colleague's brain, and we're going to be flying into our second research project. This second research project are biogenetic algorithms. These algorithms are actually in a fluid dynamic solution, making artificial nature. Biogenetic algorithms will tell us about self-organization and growth. The little bubbles that you see, the blue ones are carbon dioxide, the yellow ones are oxygen. The little plant creatures actually take in the carbon dioxide and spew out oxygen, and the little butterfly creatures grow, procreate, die, and communicate. So this is a whole balanced ecosystem that allows us to take visual and audio data from biogenetic code from our bioresearchers. Now we're going down to a 2,000 atom lattice. This is a new material discovered by my alchemist colleagues in solid state lighting and energy that like to mix elements together. And what you have here is you've got what we call the multi-center hydrogen bond. One white hydrogen atom in the middle of that isosurface bonding with 4 zinc atoms that will make a clear liquid paint that you can spray on 100-story office buildings and light up a building or power a car. These little streamer lines that you see, that's showing you electrostatic density charge. It's a new form of visualization we found for the scientists. We were able to find bonding nodes in that material so they can decide where they can make this bond occur so they can really get it strong enough to be a transparent solar cell. So the sounds that you hear are actually the emission spectrums of the different elements. Now we're going to fly into single electron spin in one hydrogen atom that's going to watch the electron jump into different orbitals into superposition. What you're hearing is you're hearing the audio of these frequencies. We're reading through what we call those streamer lines again that are passing through the wave equation and actually following the probability wave. Now, the physicists told me something very interesting. They said that the electron actually splits and goes into superposition, and it's in different orbitals at the same time. So they want to study these orbital relationships. And pretty soon, you're going to hear this pulsing occur. And when you hear the pulsing, it means that the equation has been solved in such a way that the electron is jumped into 2 orbitals close enough to beat and emit a photon. The physicists are saying they can hear photon emission better than they can see photon emission. My physicist colleagues in the Kavli Institute for Theoretical Physics say this is about as close to what it really looks like. Now, this last project I'm going to show you is electron spin. My colleagues in the quantum information processing group are actually firing lasers into a quantum dot and measuring decoherence of electron spin. We've taken the results, the mathematical relationships of their lasers, we brought them down into the audio and visual domain. You're actually watching quantum information flow. My colleagues are convinced that before they build a quantum computer and before they make a qubit, that they're going to have to simulate this. Because remember, fabrication leads to visualization, leads to simulation, and it speeds up time to discovery. So this gives you kind of a brief idea of what we do at the Allosphere instrument, how we work with data. And as I said, I've shown you a lot of scientific data, but we also work with financial data. We work with economic data as well. And it's very interesting to see the commonalities among the relationships. So now I would like to show you a little bit about, let me get rid of this one. I got rid of the wrong one. Well, that always happens. There it is. Okay. I'm going to show you a little bit about this math that I'm telling you about this conjugate space mapping that we do. And I'm going to play for you a piece by my PhD researcher, Lance Putnam, who is making this mathematics through, it's very complex. It is complex. It's taking complex numbers, doing a division of these complex numbers with a real number and the natural number, and coming up with a whole mathematical infrastructure that will allow you to map audio into visual information. So this is visualized audio right now. I'll give you 2 minutes, and you can see the tight connections coupling between what's happening in the audio domain and what's happening in the visual domain. This is the art of the 22nd century. No more are my PhDs musicians or visual artists or computer scientists or electrical engineers. They're all four. And our PhD program brings those four areas together for media representation. Very interesting. When it stops, the mathematical relationships among the frequencies are all integer numbers, which causes complete stossity. As soon as you break symmetry, you get motion. Now remember, this is not animation. This is the cold, hard math being visualized and sonified. This is our narrative. All right. And now, if I have time, do I still have time, Jim? Okay. So what I'm going to do right now is play a hydrogen atom for you. And I think you'll see as I start to fiddle with the numbers, how the numbers actually affect the sound. Now let me show you what you're looking at right here. We got a pretty benign solution to the equation. It might get a little loud. You might want to turn it down eventually, but I don't want to blow your ears out. Right here is the quantum wave equations. We've got three quantum groups of numbers. The n tells you what orbital the electron is in, how close to the nucleus it is. The L tells you the shape, what we call the angular momentum. And the J's are spin up and spin down. An electron spins on its x-axis, on its y-axis, and on its z-axis. So we're mapping about 5 or 6 different dimensions here for the physicists who want to see what they call a hydrogen-like atom with these mixtures of these particular orbital shapes that they really haven't studied in detail. And I've had 8 physicists on the bridge, 3 Nobel laureates that say this is about as close to what they see when they look at the equation on the page. So I'm going to show you different solutions to this equation, and I'm going to play it for you like an instrument. And I'm going to take that little x, y, z axis off, and I've got different solutions to the equation. This first one, the physicists affectionately call whirlwind. This is hydrogen, guys. This is what you are. We talk about understanding. And of course, I've got nicer controllers. I can use Kinects, and I can do this in the atmosphere, but, you know, in essence of time and technology, I decided just to do my little mouse thing. But let me show you what happens when I fiddle with the quantum numbers. There's nothing I can do wrong. If I do anything wrong, it crashes the system. So these gorgeous, wonderful shapes are made from the first element of the periodic table, hydrogen. My physicists said there was nothing they could learn from hydrogen, and now they're just blown away. This right now, we're just watching electrons spin, okay? I've stopped the angular momentum. We're just watching spin up, spin down of 2 wave equations. Here's another solution to the equation that they like to call momentary spires. And you're going to see as these numbers start to get more complex, the shapes will start to get more complex. and the sound gets more complex. And watch when I stop the angular momentum, and you can see these beautiful patterns occur. Now, the interesting thing is I can make 3D sculptures out of this information if I'd like to. And I could actually stop this. And I could freeze this and actually make these into sculptures with a rapid prototyping machine. Now, just so that you can understand what we're listening to, I'm reading through what we call a little polymer ring. That is following the probability wave, and I'm reading through it in the audio domain and the visual domain, okay? So I can give you an example. I can lower the pitch. So you start to see the relationships between the math, the numbers, the sounds that you hear, the visuals that you see. So you start to understand that there's a complete frequency continuum we can work with mapping, and we can make, as I said, frequency relationships in any kind of data that we have. You'll be able to use 360-degree control of sound, where you don't have to see it. It could be behind you, the information that you're looking at. Another solution to the equation. A few minutes? Okay. All right. So I will end with Ghost, which is one of their favorites. And there's no easy way to stop this equation. According to the physicist, I have to couple the spins to a spin bath, which will take about 6 more months. So I'm just going to stop it, and voila, I'm done. Thank you very much.
So take center stage, and I'll borrow the podium.